I would like to deliver general information about product itself, but my main focus will be accuracy and getting confidence into results through the meaning of practical insight into the workflow and comparing the results obtained by FEM software. I will not focus on analysis capabilities and tools that MeshFree has. My focus will be oriented to the values and the ways, or we can say possibilities, to make analysis shorten with satisfying degree of accuracy. All today's examples will be covered by linear static analysis. The analysis techniques used in MIDAS MeshFree is called implicit boundary method. This method belongs to class of the methods which are known as embedded domain methods, and other name is immersed boundary or fictitious domain. So there are three methods like that. For better understanding, let's look on traditional FEM approach. FEM has been used and is still used extensively for engineering problems, not only due to its capability to solve a high number of physical problems, but also due to its ability to handle complex geometry and boundary conditions. For FEM, as we know, the domain of analysis is subdivided into elements and resulting finite element mesh approximates the geometry, and it's used to create equilibrium equations. However, creating satisfactory mesh, the mesh which conforms to the boundaries of the domain, still requires significant user effort, and because of that, it is still the most time-consuming aspect of total analysis process. And these days, auto-mesh generation algorithms, auto-mesh generators, they have been developed that uh, in the meaning that they are working acceptably for most of 2D problems, but still can deliver not correct, let's say not unreliable results for some 3D geometries, and they are often resulting in poor or distorted elements in some regions that can lead to large error in the solution. And significant amount of user intervention is still needed to correct such problems. So some other approach rely on meshless methods. Those methods avoid some of the problems which are associated with the mesh generation by using interpolation functions uh, that that don't require connectivity between nodes. As you can see, the nodes are scattered within the problem domain as well on the boundary of the domain. And as the example of those methods, I can say about SPH, I can say about DM, EFG. That's not the point to be focused on each of them. So SPH, for example, but however, I will explain shortly. So SPH means smoothed particle hydrodynamics, DM discrete element method, EFG element-free Galerkin, which evolved from DEM, and there are also other methods. As I said, I will not talk about this, but and you can find, let's say, information about them in the literature, but generally they often differ in the method of constructing of the shape functions for the interpolation of the nodal variables. So that's the major difference. So let's back to MeshFree itself. So as I said, this method is called implicit boundary method, and the major idea is extension of or consists of extension of the physical domain of interest beyond complex boundaries into larger embedding domain of simple geometry. Simply saying, some complex shape is immersed uh, inside uh, inside a rectangular mesh. So in terms of 2D, we will deal with squares or rectangles. in terms of 3D. In 3D environment, we will work with the voxels, we can say cubes. So as you can see on the picture, some geometry, some shape is put inside those mesh. So this is how the geometry has been recognized. The MeshFree concept in Midas MeshFree emphasizes the ease of use and is directly oriented at product designers. And this means like MeshFree should make you free from the laborious process of the mesh generation and related cleanup. MeshFree uses Cartesian non-conforming mesh, which is not representing boundaries of the complex geometry. And because of that, every geometry can be correctly imported and interpreted. Let's look briefly on key differences between FEM and MeshFree. So first one concerns on boundary conditions and method of application. So we are talking about essential boundary conditions. Since the nodes are not reflecting boundary in case of MeshFree, the traditional methods used in FEM for applying boundary conditions cannot be used, and therefore other methods are required. Second challenge for accurate calculation is obviously accurate integration. And for immersed boundary mesh methods, the geometry representation, which means boundary, is shifted from the finite element mesh to quadrature points directly. And the essential idea is to simplify the mesh generation process by separating solution from geometry representation of the domain. And for this purpose, two independent discretizations are done. The solution mesh, and I will call this non-conforming mesh, and the second one, there is the integration mesh. The first one is used to approximate analytical solution. However, this mesh does not resolve the geometry of the domain. This is done by the second mesh, which is independent. So the first one is the mesh made by voxels. The second one is a mesh made by facets. So that's the major difference between two meshes. And finally, last difference and challenge for the software itself is to display and average results correctly. So the key to accuracy of numerical methods based on geometrically non-conforming meshes is domain integration methods. And robustness, accuracy, as well as computational efficiency highly depend on volume integration and surface techniques. So MIDAS MeshFree uses four methods. The first one is called adaptive ray tracing with geometry repair. So you can look and refer to the picture. So integration points will be distributed adaptively depending on the curvatures and the shape you will import. The second method is called higher order Gauss integration. The third one is the same with additional recursive octree method. So this also will make more dense integration points close to the boundary. And fourth one is called tetrahedron split. So this one is used as the backup. Actually, method number 2, 3, and 4 are used as the backup in case there are issues with the geometry itself. So in the worst case, tetrahedral mesh will be generated like in classic FEM, and this mesh will be used only for volume integration. So this is how MeshFree works. And in terms of the second mesh, as I said, the integration mesh, which is reflecting the shape of the geometry, this one is made by 2D facets, which are simply saying triangles, so you can see on the picture. And the method which is used is simply conducted using Gauss quadrature on the geometry. So you can refer to this picture. I also presenting octree method in terms of 2D. You can see that number of the grid is going to be lower at the center of the geometry. Close to the boundary, we can observe much more voxels. So the grid displayed by MeshFree is presented to the left. So we cannot see voxels directly. We cannot see to the facets. And the reason is we want to avoid excessive dense of the blocks to assure good visibility of the mesh and geometry itself. So that's the simple grid that you can see inside the MeshFree. So now we know how the MeshFree works, what is MeshFree. So what you should remember, there is no traditional approach inside the software, and convergence will be achieved independently on the shape and quality of the element, since there is no traditional mesh. There is a simple mesh. As an illustration of what I said before, let's look at simple example of the component with large number of the details. So the meshing of such geometry is not always successful. It's also necessary to carry out a process of elimination of those details. And what is important, we always need time for all of this. So then, even if we manage to create a mesh, there is a still risk that the values obtained don't always appear where we expect. So you can see we are expecting stress at the place where we assign boundary condition, but maximum appear in different location. So cleaning the geometry, remeshing and analysis, this whole process can took some time. So I'm just presenting as average for the example. Let's say for this example, the total time was 3 hours. And as you can see, a lot of elements has been used. So this requires a lot of work. Even if we use auto measure, we can meet a lot of obstacles. So cleaning geometry is a process that can be really tough, and its success rate is not assured in every case. So in many cases, this is a most consuming process and requires the user's understanding of the tools. We have to make a plan for the cleaning and the repairing of the geometry. So by the cleaning, my understanding is not usage of the tools only, but making a plan, the whole process. Like we will use also other geometry manipulation tools. Geometry has to be cutted, faces will be exploded, stitched, merged again. I mean, and then we can combine those tools with traditional geometry cleaning tools. So all of that will take some time, and frustration generated during this process can get high level, let's say. Okay, now let's look on the simulation with Midas MeshFree. Let's look on the video. Let's click on new file. As you can see, the first step is to select the analysis type. So for my demo, I'm clicking on linear static. Then second step is geometry import. I will import the same detail which has been presented on the previous slide. So the next step, material assignment. You can do this in several ways. You can use right click, as well as you can drag and drop on the geometry. And the third method is to use define material. And now what we can see is the material manager. So you can select material from the database and assign into the part. So the next step is constraint condition. I'm selecting faces, and just to speed up selection, I'm clicking on the option which is called select tangent, and I'm applying load. So what we can see now is geometry. As I said, we cannot see voxels, we cannot see 2D facets. We are seeing geometry now. So I apply the low. I'm using cube as the reference for global access. Now I am displaying window where you can preview your your mesh, the simplified mesh. So what you can see is the number of the blocks, and I will back to this topic later. I'm clicking main control button, and because of that I can use a setting which refers to how much RAM will be used for my calculation and how big will be my model in terms of the number of equations. So this RAM slider is strongly connected to the number of equations. So now solution started. At the bottom you can see solving status. Calculation took a little bit longer time, so this video has been edited by myself. And now let's display results. So now I'm showing stress von Mises contour, and inside MeshFree you can find the tools which we are familiar with already comparing to other FEM solutions. So you can use contour maps, you can prepare animation. Now the color method has been changed to free. I'm changing the legend, so I'm manipulating with number of the points after the comma. We have also clipping planes, so you can create sections, and it's also possible to display point values, and I will do that in a few seconds. So just let's go to point value command, and if you want to display value at any location, just click on it. It doesn't matter if this is placed from the section or not, so you can pick. As you see, geometry consists of geometrical details. There are a lot of curves, a lot of issues, and now I'm displaying graph on the geometry. If you want to see how some output value vary along the length, you can use this command. So that's more or less how simulation looks like. So it took 3 minutes with calculation 4 minutes, and you don't have to be focused on the mesh. So as I said, the major topic of this webinar is accuracy. So then set up the model size is very crucial, and how to do that in MIDAS MeshFree. So we have two methods. We have automatic approach and we have manual approach. So starting from manual, which is the easiest, so please look to the right picture. When we click user-defined option, we can set up number of the blocks along X, Y, and Z axis. And because of that, our model will generate appropriate number of equations since we are using adaptive method. Okay, so we have control only on the blocks, but this blocks is a reference measure how big will be the model. So we can do this manually and we can do this automatically. So if you want to use automatic approach, then you can click automatic option, and this has been presented to the picture to the left. And another command which is connected to automatic approach, as I said before, is the slider which defines how much RAM will be used. And as I said, this number of gigabyte will define number of equations. So if you decide to use 2 gigabytes, then approximately 2 times more of equations can be generated, but also it depends on the geometry. So it's not always proportional. Only for simple geometries will be proportional. So you can decide how much accurate your model will be. Of course, analysis solution time will be extended. So we have to learn how to do this wisely. So not always 5 or 10 gigabytes is enough, or will give you accurate result. You can get accurate result using 1 gigabyte or 2 gigabytes, and we will see how to do this. But still, before I will go through the next pages, uh, I would like to emphasize that automatic approach is still the best, and it offers the optimal size of your model, so don't forget about that. So how to measure energy? How to measure error? I'm sorry for that, I just said. How to measure error in Midas MeshFree. So basically, we have to go to the tool which is called strain energy error analysis, and we are measuring uh, discretization error, which is error connected to strain energy. So there is a table which is made for single part and for the assembly, and we have to learn how to get valuable data from this table and to estimate when to stop uh, our solution, when our model is convergent enough to stop and accept the results. So that's the table which will be helpful. So just to remind to some of you, what is the strain energy density? Basically, it's defined as the strain energy per unit volume, and this is great indicator since even if you look on this simple equation to the bottom, the size effect is eliminated from the investigation, so we can focus directly on material parameters, and this is why also it can be used as the universal, let's say, indicator to check for many components. Okay, so let's do some tests, and let's start from simple cases. I'm presenting now the data for the models I will be used. So I will use simple geometry. We will conduct simulation of tensile elongation of the circular specimen. I will start my tests from automatic approach, and I will use 1 gigabyte of memory to create appropriate number of equations. Okay, so after calculation, this is what we got. So we are expecting that maximum stress will be around 12.73 megapascal, and I got it. Stress distribution is okay for both of the cases. If you take a look on the solution time, you can see that is pretty much comparable, almost the same, as well as number of the equations generated by automatic algorithm is almost the same. So for circular section, as I said, we are, let's say, shape. It's not so much important for MeshFree because adaptive algorithm is distributing integration points adaptively. And what you can also get from this slide, you can always check how many blocks has been generated by automatic measure, let's say like that. So you have to go to the bottom of the MeshFree, to the left bottom corner, and display this window, so you can find this information. As well, you can go to folder where you stored your model, and you can use text editor and open the file, and you can then you will get information about your model. So total error is approximately the same, and I will back soon to this table, which is now, because now I would like to say a little bit more about values which are used in this table. So we are starting from the mean strain energy. So basically what we can see, the table is prepared for parts and for the assembly, and what is most important is to figure out how those values are calculated. So first of all, if you take a look on total strain energy, and when you get this value and divide this value by the volume, then you can get this value, mean energy density. So this one divided by volume means this one. And in similar way, if you get total energy error and you will divide by volume, you will get error density. So all of equations has been presented, but what is most difficult at the beginning, at the first contact with MeshFree, is they are those two columns. First one is called percentage energy and percentage energy error. So how to understand those two columns? So in case we are dealing with single part, this column, percentage energy, is saying how much energy has been accumulated inside this part, how many percent. So since we have one part, 100% is accumulated. In the same time, because of that, 100% of error will be related with this part. So total energy error is this one. So we can say like this error is error accumulated for that part. So 100% of total energy error is distributed to this part. So when we are dealing with assembly, this value will be proportionally or not proportionally divided depending how much energy has been distributed. Okay, so to summarize, automatic option will generate the most optimized mesh size of the model. So please don't forget about this, since we have to estimate correct stiffness distribution and assure accurate stress distribution. This option will always set the most optimum number of the blocks for your model. So let's check why it's like that. So let's start from a manual approach and let's conduct some tests using the circular and rectangular specimen. And what is the minimum number of the blocks? It's 1, 1, 1 across all of the axes. So let's investigate results for this case. From theoretical approach, I'm expecting that elongation will be 1.27 millimeter, and for both of the cases I got a result which is pretty much convergent because I get 123, and for rectangular section I get 1.27. So I still I can say that this is accurate response of the model in terms of the displacement. But how it will look in terms of stress? So if we look on both of the tables, normalized total error is around 12.7%. So for the simple geometry and for those setting, which was 1, 1, 1, number of equation for the both cases is 60. Solution type is really short. So now we can figure out that this is a strong correlation between sizing of your model. But the stress distribution itself is wrong. So we are expecting a uniform distribution along the model, but also the values are totally different that we are expecting. We are expecting 12.73, but the maximum value is 14, and additionally it's not a uniform distribution. So this is totally wrong result in that case. So if we do the same example for the bending case, situation looks much more worse. So definitely using the size 1 by 1 by 1 in terms of stress is not acceptable for both of the cases. we can use only for simple elongation stress and use proper boundary conditions. So we have to figure out the stress condition inside your specimen. Then we can use one element along some axis, but generally it's not recommended. We don't know how which kind of stress will be generated. So I'm just showing this to you when how to set up the model and which size should be avoided. So one by one by one is not recommended at all. So let's change the number of the blocks along y-axis to 5. So now you can see that stress distribution starts to look much better. We have 12.73 value. It's much more uniform, but maximum value is not at the boundary location, which means it's still wrong. The distribution is still wrong. However, normalized total error decreased drastically. Now we have from 12, now we have 4.96, as well as total strain energy value increased. So now I'm talking about those values. This is 630. Normalized total error is 4.96, and also those values um, went lower, excuse me, went lower. So let's do another test. Let's increase again along y-axis. So now the number of the blocks is 20 along y. So what happened? Stress is much more uniform, but still we have maximum value here. Now total normalized error is 1.61. Total strain energy is 633, which is close to the theoretical one. The next case shows shows the model size 5, 20, and 5 for the zeta. Total error again 1.83. Strain energy value is the same, but we still got the maximum point not in the correct position. So let's make another test. This time let's increase along y and change as well on on the section. Actually, on the previous model, as I'm presenting now, we change the size across the section. So now I'm increasing along the length again. So what actually happened? Now I got correct stress distribution. Maximum value is close to the constraint, and total normalized error went down. So now it's 0.82. And the question is when to stop. This is what I was saying at the beginning of this presentation, when to stop to do those tests. Yeah. So let's do one more example, this time with 100 elements, and total normalized error went down, but not so much. So what we have? So let's look on the next slide and let's compare all of those results. So we can see together that von Mises stress starting from the second example was the same, but stress distribution was not correct. So stress distribution started to look correctly from the two last examples. So when you go there from 555 and for 5 per 100 per 5, for those two models, we got correct stress distribution as well as values. So mean stress, mean energy density was always correct. We can say the value we are expecting was okay. Strain energy was okay. Errors was going down all the time. Yeah. So the question is when to stop. So if we compare this with automatic grid setting, which I was presenting at the beginning, we can see that difference between the ratio between mean energy density and mean error density is approximately 1.5 multiplied by 10 to the power of 4, which means there are 4 orders of magnitude of the difference. And that's actually my tip to all of you. When you are working with MeshFree, you have to look and compare those values as well as a reference to the total normalized error. So if this error, if this ratio is like 4 orders or higher, then we can expect our model is accurate. And let's look on another examples. So let's compare this value with FEM. So as you can see, both distributions are the same, and I used Midas and FX. I created mesh manually, so now I'm sure that this value is correct, but still the question is how much and when to stop. So if we go to this table and if we compare the value with my statement, you can see like there are 4 orders of the difference, and because of that I can accept this model, so it's correct model. Of course, at the boundary location place, this is a singular singularity point. So if we start to make the elements smaller in terms of MeshFree, then the value will get higher. So we have to also stop at some moment. So now let's compare with another model, the last one, where we got 19 at the peak. So the same situation if you cut your model when you make elements more dense close to the boundary, you will get the same value, and this works for both type of the elements. So this analysis has been completed in 1 second, this one 0.2 second longer, but still we have to remember like we did almost nothing there. And there, if we want to make accurate result, we can use, of course, automatic measure. This is simple geometry, but this is not the point. We have to still do some effort to prepare this the mesh like that. Here we can focus directly on the value. So in terms of the bending, let's compare all the result. So in terms of the value, you can observe like for my last models, the value is correct everywhere. We can say it's the same, but there is a small difference in terms of the stress distribution. So using the same approach, we can see how much error has been generated, what is the ratio, and use your investigation. So I'm just investigating my manually created meshes. So those models has been made by myself, and now let's compare with the automatic setting, and this automatic setting generated this size. So my last choice was 10 per 100 per 10, but computer made 12 113 12, which is almost the same, but comparing with the error, it's almost the same. So my model, I can say, and automatically generated model are pretty much the same. So the values are the same with like comparing with FEM. So there is the same value, the same maximums are almost the same, and deflection is the same. So this statement is correct, and this is clue that this is the tip for all of you. So now let's look on the example. So I will play video with the example which will present practical approach. Okay, let's open the MeshFree and let's import the geometry. So this process will be repeated. I'm going to import tool and I will open the geometry. So now I'm working with MeshFree 4.0. So as you can see, user interface has been changed, and now I'm saving my model. A model will be constrained and loaded in very simple way. So I will constrain the holes. Now I'm presenting the feature of the automatic contact. So in terms of the assembly, contact is automatically generated. And the first step is material assignment. So now I'm presenting first method. I just clicked on the part inside the model tree. Now I'm using define material window, and now I will assign from the user interface. So you can click on the part and right click on particular part and assign the material. So let's apply boundary condition. I will change selection to type to circular. So from this point of view, I selected all of the faces from the holes. And let's do the same with tangent faces. Let's apply the load. So as the first loading, I will use force. So this force will be parallel to X axis. Let's click OK. And as the second type of loading, I will use pressure, 0.5, and I apply it. So inside MeshFree, there is no geometry editor. So if you want to apply loads and boundary conditions on specific faces, you have to use imprint command inside your CAD modeler and then import to MeshFree. So for this model, I will use automatic approach. Oh, excuse me, I will use manual approach. So that's the tip for you how to deal with the model when you want to do on your own. So now let me show you what I did. So I will stop for the moment. So that's my tip to you as well. So for each model, for each assembly, I'm starting from this setting. Like I'm setting 10 blocks everywhere on each direction, and then I will I will do first initial calculation, and then I will check the stress strain energy distribution. So that's my approach. Oh, sorry for that. So I will simply go to this place, and now oh, let's see the same. And if you want to display grid, just double click on the geometry. And let's start calculation. So this time I will not cut this video, so it's not speed up. This is the original calculation time. So it's, as you see, it's very fast. Let's change the display method. Let's click on undeformed, and let's finally go to strain energy error analysis, and what we can see, that's 30% of the error, and most loaded part is a part which is called bar 1. So for that part, how much energy is accumulated inside this part is almost 80%, 79% of the total strain energy this part is handling, and total, let's say, error which is related with this part is 66% from this one. So as I said, the difference between those values is small, it's only one order. So we have to make model more accurate. So now I know which part at which part I should be focused. So because of that, I will go and save my model, and now I will change the model size. So sorry for that. Oh, that's my setting for the bar 1. So this is 30 blocks on X. 100 blocks along y and 30 along zeta. So that's how my mesh looks like at this moment. And I will do calculation. So when calculation is over, let me display the result. So now my energy error went lower, and there is almost the same result for the energy distribution, so 83%. Now my error is approximately 3 orders of the difference, so I can assume like this result is much more accurate, but still normalized total error is close to 10%, which can be accepted, but it requires some experience from you. So let's see the comparison of the result. So this is exactly what I got during my study. So calculation took 41 seconds in total. That's the table, and let's compare with FEM. So comparing with simple mesh, simple hexa mesh that I prepared manually for this model, and I made 3 elements across thickness. I got those results. So the results are very similar, as well as distribution of the stress is also the same. Okay, so let's make it more accurate and let's compare with automatic approach. So at the top, I'm presenting my model, which has been calculated in 41 seconds, and in total, uh, uh, including my calibration model, I think I spent 3 minutes, kind of that. So when we approach this model with automatic setting, so I was solving this model with 4 gigabytes. That's the number of the blocks generated. I got much more lower total value, almost the same distribution in terms of energy density and error, almost the same. And then we can compare values. So as you can see, MIDAS MeshFree is very accurate. The whole point is about how much accurate stress distribution we want to get, because in terms of value, it gives accurate results. So there is a model for comparison. I was using 4 elements along the thickness, so it was really big model, millions of elements. So the accurate result, let's say, is 22.96, but for both cases from MeshFree I got 23, which is excellent result. So let's do something more accurate. And finally, for this part, my setup was like presented on the slide. So it was the same, but I was using option which is called representation detail. So it defines additional correction for the curvature for the curvatures. So that's the perfect example, since this is a circular pipe. So I was using the most accurate setting, and because of that, my total value went to 3%. It's almost 4 orders of the difference. As I was saying before, 83% energy has been accumulated, and at this point, my calculation is over. In terms when in the case when I want to play with MeshFree by myself, but still, I think mm, I think it's good solution. So there is not so much significant difference. I'm just showing this to you just to make you sure that stress distribution generated by MeshFree is highly accurate, and you don't have to spend time to think how many elements along the thickness and how much your model should look like in terms of the size. So that's the automatic approach. The second example with welded contact. So I'm not presenting video this time, but the same with welded contact. If we look on the part which is called body 1, then we can see almost the same difference ratio. And from my point of view, this model the calculation of this model is done, so it gives accurate result. So how to analyze faster? As I said many times, automatic grid setting creates most balanced model size just to assure optimal settings for stiffness and accurate stress distributions. Manual approach can speed up solution drastically, but you have to spend some time for the calibration. And uh, when your estimation of the cells will be wrong or not enough, this can lead to non-accurate stress distributions, but only stress distribution, not the value, as I said. And in the terms of stiffness, you can still get correct stiffness distribution. So this also creates some kind of way or approach for high number of for them dealing with assemblies with large number of the components, because you can estimate, you can exactly tell to the software at which part you are expecting to get accurate stress distribution in the same manner like for classic FEM approach. So we are doing convergence study. In this increasing memory for auto setting also is not convenient all the time. It increases calculation time. Uh, so my recommendation is to use the number of months from 4 to 8 or 16 gigabytes if you can, but not lower. I would like to, my advice is to focus on the part which requires improvement in terms of the number of the blocks, and then use auto setting for the rest of the parts. But it depends. So that's the general conclusion, that automatic is still the best, and now I think you understand why. So if you want to be sure what is the accuracy level of your model, as I said, 4 or 5 orders of the difference will give you excellent accuracy for the part. For assembly, it will be almost the same. Generally, if this ratio is higher, then the accuracy is also higher. Uh, and all of values should be compared with total normalized error, and the general rule of thumb is that less than 10% is recommended for designer purposes. So that's the approach that we are using. So some examples. So you will see the value of MeshFree when you will start to do models with high complex geometry, when the number of the details will be really high, or when the large number of components will be present inside your geometry. So that time MeshFree is absolutely amazing. Another example is complex piping system, and another example is frame. So if you want to do this by beams, I wish good luck. It will take a lot of time starting from neutral axis generation, so you don't have to do that. As well, if you want to do this by solids and get accurate result, you have to spend a lot of time. Okay, thank you so much for joining today's webinar.